Here I will demonstrate the appearance of a limit cycle in the FitzHugh Nagumo model. The model is shown here in an ODE file where we see the equation for dx dt and alongside it the equation for dy dt. Notice that dx dt is a cubic curve. Let us start our XPP for this file, and the first thing we'd like to see is the nullclines. So let's, as usual, make nullclines appear by typing NN. And what we'd like to do is get as close as possible to a steady state at the intersection of those nullclines. We can do that by picking initial conditions with the mouse that are close to that steady state, and then typing IL a couple of times for initial conditions last. This will allow us to converge to that steady state and be assured that auto will start from a steady state value. Next, let us bring up an auto window by pushing File and Auto. So here comes that window. We will produce a bifurcation diagram with the parameter A. So we click OK, and then we pick the axes, which we'll here choose to be high-low. The y-axis will be the steady state value, x, and the main parameter is a, so these two lines don't have to get changed. Now, the value of a only makes sense when it's positive, and so we'll set the minimum value along the horizontal axis to be 0, and the maximum value we'll set to be equal to 1 in this case. We'll leave the minimum on the vertical axis as it is and click OK. In the numerics panel, there's not too much we need to adjust other than the minimum and maximum value of the parameter. Let us adjust the maximum value of the parameter to be 1. Now, going back to our XPP window, let's have a look at the parameter values. Currently, A is 0.7, and so what we'd like to do is ensure that when we integrate, we start with a minimum value of 0.7, its current value, and allow it to integrate up to some maximum, such as 1. Click OK, and let's run steady state. And you'll see that a solid line appears indicating a stable steady state with one point marked with a cross on it. We're going to grab that point by going to grab and hitting enter. And now we're going to integrate backwards to see the value of the steady state in the opposite direction. To do so, we go back to the numerics panel and we change our step size from ds being positive to negative to integrate in decreasing values of the parameter a. Moreover, we now change the parameter minimum to be 0 so that the integration, the continuation rather, will take place all the way down to 0. And when we push run, we see that this completes the diagram. We also notice that there's a change in the kind of line from solid to slightly less bold line, and another point appears. We'll go through the same exercise of grabbing points by tabbing, hitting the tab key until we arrive at this new point, and observe when we do so that in the lower panel here we see HB, which stands for Hopf bifurcation. We push enter to grab that point, and now we run periodic, and there, voila, we see a Hopf bifurcation indicating that a limit cycle exists. The outer dots indicate the amplitude of that cycle, and we see that it appears quite suddenly in its full amplitude. Now let us go back to our window our XPP window and select a parameter value such as a equals 0.2, for which we know a limit cycle exists. Let's erase our diagram, redraw the null lines, and now let's have a look to see what sort of dynamics we've got here. So let's start with any initial data, and lo and behold, here is our limit cycle.